I clicked go live. Go live. Going live. You're live. I hope it's working. Maybe you can just say in the chat if you can see me and hear me okay, and then I'll begin. Just a few people let me know that the stream is working all right, and that you can see me and hear me all right. Yeah, great stuff. Okay, let's begin. I hope the audio quality is a bit better. I got a new sound card, so I hope the audio quality is a bit better than when we tried to do this last week. So I'm going to switch over to doing this thing. Okay, which is to show my desktop with the little camera thing in the bottom right hand corner. Okay, awesome. So it looks like everything is working. Hooray! A new toy, a new thing. All right, everybody. So we're working on Boids in ECS. I hope everybody has taken the time to look down through the source code a little bit and get familiar with the principles behind how ECS works, and then also, you know, how, like, we've taken the, you know, example of Boids, which is like this algorithm which is like normally of O(n) squared complexity, you know, and then once you keep on adding Boids, like there's a limitation definitely in this example here of just how far you can go with mono behaviors. Like with mono behaviors, you can simulate about 600 Boids because everything is happening on the main thread, and then the FPS starts to drop, right? So with this example here, I can simulate up to 25,000 Boids with a simple procedural animation on them as well. So like it really scales up, like it's orders of magnitude faster when you write things using ECS. And even though it's in beta, like or alpha, you know, this is going to eventually be the way code is written in Unity in about, I'd say, a year or two. So anyway, here's the Boids example. One more time, we get a chance to look at the Boids. These are, like, say, 1,000 Boids with a trail which is made up of 25 entities, and then a procedural animation on the head and the tail. And like, what were we saying about this? Okay, so there's lots of different parameters we can adjust on this thing. I'm not going to do them all because I've done all of that in lots of other videos. But something I think I forgot to show you the last time in the last video was this, right? And it's the importance of like understanding data structures and algorithms as well. So I'm going to spend some time today talking about like what data structures and algorithms you use to implement something like this. And if you actually look at Unity's implementation of Boids, which is one of their examples that comes with the ECS examples, they also use this data structure, you know. It's called a native multi-hash map. And if you do this particular algorithm, which is called a cell space partitioning algorithm, you can look at what FPS I'm getting now. So I'm getting like 90 FPS when that algorithm is turned on. But if I turn that algorithm off, the FPS drops down to like, you know, maximum 40 FPS, but really, really slow. So the FPS is, you know, there it is down to 20 FPS. So that's 3 times slower without using this algorithm. You turn the partitioning, the cell space partitioning algorithm on, and the FPS like doubles or triples. So I wanted to show you guys that. Okay, so this is Boids using ECS, and like there's lots of useful things that I learned in programming this that you know, I've kind of like identified in those 30 questions that I wrote. So let's see if we can find answers to those 30 questions. Let me get this going here. Where's the website? Here we go. No, Game Engines 2. Awesome. Here we go. Here are the 30 questions. Flocking in ECS. So we started these. We answered the first few of these last week, but let's just briefly mention them again. What are entities, components, systems, and jobs? Entities are basically, there's a struct called entity, and an entity consists of an entity ID, which is an integer, and a version number. And like conceptually, entities are containers for components. In reality, what happens is all entities which have exactly the same components on them get stored in the same contiguous block of memory, because the principle is that when you're iterating over entities, if you iterate this entity, you're going to want to iterate the next one and the next one and the next one. So they're all stored contiguously in memory. And that's what an entity is. A component is a subclass of iComponent data, and it encapsulates the variables that each entity has. So you might have a component which is the entity's position, and that's called a translation, or it might have a rotation, or it might be a particle, or it might be whatever. So the actual data that would normally go into fields in a mono behavior go in and become fields in a component which gets associated with an entity. A system is a subclass of system base, and a system, basically systems get started when Unity starts by default. You can say don't start the system, and the system is a subclass of system base, and it gets various callbacks from Unity. So there's on created, on destroyed, and then there's a method called on update that you override the on update method. So it's an example of polymorphism. It's an example of polymorphism in action, because you have to put the override annotation into the code. So system gets an on update method which gets called once per frame. Usually systems iterate over entities and do things to entities. So in order to do that, systems typically spawn jobs. And jobs are the other thing that goes along with dots in Unity. Jobs are the ability to write code that gets executed across all the cores and threads on the CPU that your game is running on. So like this thing can do like 16 or whatever number of things at the same time. Unity has this job system which keeps 16 threads running at all times, waiting for jobs to be submitted, and then they take the jobs off the job queue and they run them in parallel then across all the cores and threads in your CPU. So systems spawn jobs typically in order to update entities. That's the definition. What is the purpose of the class Boid Bootstrap? The purpose of the class Boid Bootstrap, let's open it up here and take a look. This is the ECS examples code here. Let's look at the Boid Bootstrap. So the Boid Bootstrap is like just a kind of like, it is a way of getting stuff from mono behaviors into the system. The Bootstrap can create all the entities, or the Bootstrap can just like hold some values which maybe you want to adjust in the Unity editor or whatever. This thing here creates all the entities. That's number one thing that it does. And number two, it like feeds values from the fields in Boid Bootstrap into the system in order to adjust the system as it's running. So things like the speed of the boids, the weights on the different behaviors are stored in the Bootstrap, and then the system picks those up. So that's the purpose of Boid Bootstrap. So you're often going to have things like this, you know, things that like work between the different worlds, the entity world and the mono behavior world. All right, next question. In the previous example, we explored two approaches to creating entities. Describe them, which approach is used in the pure ECS scene. So the two previous examples we did were the life system, and we also did the, what did I call it? It's the noise, was it the noise system? I think it was the noise system. Or what did I call it? The voxel terrain. Noise cube? Must be the mesh controller, the life system. Well, the life one was one of the other ones we did. Actually, the life one is a good example as well. In the life one, we created all of the entities in a batch. So there's an API call on the entity manager called create entity. And yeah, one version of it takes a single archetype, or the other version of it takes a native array, which is one of the native data structures, and it will create the same number of entities as there are in the native array. So it's one API call, and it's really, really fast for creating entities. That's what we did in the life system. What's happening in the Boid system is we're actually creating the entities one by one. And this is the other way of creating entities. So inside a loop, you can create your entity, assign all the values, and so on. So there's two approaches, either in a batch or one by one. If you're doing them in a batch, it's obviously a lot faster. But then maybe you need to spawn a job to populate the entities, which is what we did for the Game of Life and the Spiral thing as well. So that's the two approaches to creating entities. What we are using in Boyd Bootstrap is we're using the approach basically that creates the entities inside like a for loop on the main thread. So that's why when you click play, there's a little bit of like lag while all of those game objects are being created. 28,000, not game objects, entities. While all those 28,000 entities are getting created one by one. So that's the answer to that one. Okay, in the previous example, we looked at two different types of jobs. What were they and what were they used for? Well, we looked at entities dot for each. So entities dot for each, let's see what does that, let's see, there's the life system. The life system actually spawns both type of jobs, so it's a good example. This is type of job number 1, which is an entities dot for each. So here's the entities dot for each. And you write your method signature like this, and it uses a lambda. So a lambda basically being a block of code. This is the symbol for a lambda here. And basically the method signature must, like it can take, or like if you use this version of it, it takes entity and query index. And then this is what's called the implicit entity query. So this will retrieve all entities with cell, translation, non-uniform scale attached, and iterate over all of those entities. And then you can like assign values to those components on the entity. So that's one type of job, which is an entities dot for each. The other type of job that we made was something that doesn't iterate over entities, but just iterates over native arrays. And that's an example of this type of job. So to do this type of job, you subclass iJob parallel 4, and then you schedule the job like this. You have to assign these fields on the struct, and then you schedule the job like that. So that was the two types of jobs that we looked at. We looked at ones that iterate over native arrays and ones that iterate over entities. And you can mix and match those in various different ways, and you can combine all the dependencies and say, this job has to execute before this job, and so on. So that was the two approach. What approach was used? Oh, here we go. Boids system schedules a third type of job. And they're called iJob entity batch jobs. What are these, and how does this approach differ from using entities dot for each? So entities dot for each is like the fastest, the way to write the job that iterates over entities with the minimum amount of code. But it's what's called a lambda, and there's certain limitations with how you use lambdas. One of them is that it can only operate on local variables, which isn't generally a problem. It just means you have to like copy all the field variables into local variables, and then they get picked up by the lambda. I discovered there was a problem using the native multi-hash map using entities dot for each. I couldn't figure out how to write to it in parallel. I kept getting errors, so I had to look at another way of iterating over entities. And the other way to iterate over entities rather than use an entities dot for each is to use, like if you look at the Boids system, this thing here, which is the third type of job. And to do these third type of jobs, you extend iJob entity batch. And this is like similar to an entities dot for each in that it will iterate over all the entities, but it's a struct. It doesn't use a lambda. So you don't have like the limitations of using a lambda, which are maybe the local variable capturing, and also that problem I had with basically iterating over the native multi-hash map. So that's an iJob entity batch, and this is the way you set it up without getting into too much detail, but basically this also iterates over all the entities, but it uses a struct rather than the lambda approach. And other than that, it does the same as entities dot for each. It's a different way of setting up your code to iterate over lots of entities. Cool. So that's the third type of job. So you've got entities dot for each, you've got iJob parallel 4, and now we have iJob entity batch. There's actually a ton more of them, but they're the three that I have used. And like you get a sense for what they're used for. Entities for each is used to iterate over all the entities. iJob entity batch is also used to iterate over the entities. iJob parallel 4 is used to iterate over native arrays. I hope you're all taking notes. Okay, how did these jobs select entities to iterate over? They select entities to iterate over by using, you might remember this, an entity query. So let's see, cohesion job. Entity queries. Entity queries are these little structures that you set up to say, give me all the entities with these particular components attached. Let me have a look at that cohesion job. Cool. So here's the cohesion job being created. And here's the code to actually schedule the job. And you can see that the first parameter is this thing called the cohesion query. And this is a cohesion query is an entity query. So an entity query is basically a thing that you can use to say, give me all the entities that have this component. I want all the entities that maybe don't have a particular component. And so this basically retrieves all the entities that have the cohesion and the boid component attached. So that's how they select entities. What is a native container? Give some examples. What native container does Boids system create, and what are their purpose? Okay, so you might recall from previous classes that you can't use arrays inside jobs and inside the whole ECS world. Why can't you use an array? Because an array is a reference type. It is a pointer to a location in the computer's memory, the same as a class, and it has methods on it, right? And for various reasons to do with type safety, jobs can't use reference types. They can only use structs. So Unity has provided this new library of containers. So things like arrays, lists, hash maps and stuff like that. But they have a different name. They're called native array, they're called native hash map, they're called native list, native queue. All these different data structures are in this library. So that's what they are. When you're in the ECS world, you've got to use these data structures rather than using arrays and things like that. And that's what their purpose are. Oh, they can only store what are called blittable types. So a blittable type is like something like either a primitive type or a struct. Remember we talked about the difference between structs and classes. So that's a native container, and that's some examples. What native containers does the Boids system create, and what is their purpose? Well, let's have a look. The Boids system creates a native array to store the neighbors. Okay, it stores a native array, have all the positions, a native array for the rotations, a native array for the speed, and then a native multi-hash map. So hash map, you guys know what a hash map is. It's key value, multi-hash map. You can have multiple keys and multiple values. So that's a multi-hash map. So they're the data structures, they're the native data structures that the Boid job system creates. You will, if you do ECS, have to create these as well. That's the way you know, because like you can't use arrays, you got to use these data structures. This thing here is used for the cell space partitioning algorithm. Positions and rotations are obviously the positions and rotations of every Boid, and they're stored here because like every Boid needs to count its distance to all its neighbors, and in order to be able to read out of order, I actually read them from a native array rather than read them directly from the entity. So that's what their purpose is. What jobs does Boid system schedule, and in what order? Is this order significant? Yeah, it schedules lots of jobs, and I wrote this because originally I thought, well, okay, this is going to be a whole Boid system, so sometimes some of the Boids will want to do different behaviors, seek and arrive. So you only want to calculate the behaviors for Boids that have those components attached. So basically I separated each of the behaviors into its own job. And of course the order is significant because you have to evaluate them. Some things need to happen after, some things need to happen before other things. So if we go into Boid job system and we look at the on update method here, you can see the order of the jobs that are executed. Hey, let's take a note here because like this is kind of useful. Let me take a note. I'll just take a note straight into the code, right? The order of the jobs. The first job is copy to native job, right? That's the first job. let's look what it does. Copy transforms to native job. If I go to definition here, it brings me into this thing. So this is the iJob entity batch. It's going to iterate over all of the entities. Same as the entities dot for each. And what does it do? For every entity, this is, never mind about all this is coming boilerplate code to set up the iJob entity batch, but this is the core thing that it does. It copies all of the translations and all of the rotations from the components into the native arrays. So if there's 1,000 boids, the size of these two native arrays is going to be 1,000, and every frame, their translations and rotations get copied into a native array. So like again, for boid number 999, array element 999 is going to have boid number 999 in there. So that's the first job. The next job that gets executed, let's go back, I should have split my code here. COPYT, here we go. That's the first job. So every boid's position and rotation gets copied into an element in a native array. Next job that gets executed is the obstacle avoidance job, which doesn't work. Maybe it'll work tomorrow, because I think tomorrow we'll talk about obstacle avoidance. So the obstacle avoidance job, the next thing that happens is the cell space partitioning job gets executed. If the flag is enabled, the partition space job is the next one that gets executed. Space. So partition space is the next one. Next one that happens is count neighbors. And then you have probably the next three jobs are going to be separation, cohesion, and alignment. Oh, constrain is the next one. So that keeps all the boids swimming inside a certain area. Separation, cohesion, alignment. So let's put those in the list. So we've got count neighbors, then we have separation. Separation, cohesion, alignment. I'm sure there's probably a few other ones. Oh, wander is probably going to be next then. Wander, and then the boid, and then the copy from, okay? And then the boid, which is the integration function. And then the copy from. Cool, so that is the sequence that the jobs are executed. And, oh, this is so important. When you want jobs to get executed inside a system in a particular order, so basically copy to natives has to happen first, because all the other jobs depend on those native arrays being set up. And then these jobs, obstacle avoidance, partition space has to happen before cohesion and alignment and separation, and so does count neighbors. These two things have to happen before these jobs get executed, because these jobs depend on every neighbor knowing, every boid knowing which other boids are its neighbors. And then wander, finally boid. All of these have to happen before the boid, because all of these generate a force, and then the boid is the thing which is going to sum all the forces up. Yeah, the YouTube streams are recorded as well. I'll make the stream available on the Git repo of the course after this class. Yeah, of course they're recorded. Okay, cool. So, obstacle avoidance, blah, blah, blah. Partition space, count neighbors, that's the sequence of the jobs. And hopefully you see why they have to happen in this order. I mean, it doesn't matter whether you do cohesion or alignment or wander, or these ones, but you have to do all of the jobs. You have to do all of the jobs before you do the boid, because these are evaluating forces. This is going to integrate the forces. And you have to do count neighbors before you do separation, cohesion, and alignment. Now, just to show you guys, this is the way you combine jobs together. So when you schedule a job, you get back a handle, and then this is kind of like boilerplate. You go dependency equals job handle dot combine dependencies. You pass in this dependency, which is a field in the class, and you pass in the new thing that you get, the handle that you get back. And so you can see every time I schedule a job, I basically call this combine dependencies method and throw in the dependency, throw in the job into the dependency list for this system. Alrighty. So that's how you combine all the jobs and you say that they have to happen in that particular order. Next thing. Partition space job uses an algorithm called cell space partition. How can the algorithm reduce computational complexity of flocking? Okay, I'll draw a small diagram for this. Even though I kind of drew this at the start, so you guys might remember I did think this diagram already, but just as a little refresher, because we're doing these questions, so that you know. Again, if you ever wanted to implement Boids, this is an algorithm that you need to understand. I think that's my diagram from the last time. Alright, I'll try and draw a diagram here. Turn this thing over. Oh, I need to bring it onto the other window. That would be a good idea. So imagine you have a whole lot of Boids. This Boid, we've got this Boid over here, we've got this Boid heading in this direction, got another little Boid over here, got another one over here. Every time we add a Boid to this thing, it kind of squares the number of calculations that need to be made, because this Boid needs to get the distance to here, the distance to here, the distance to this guy, let's put another Boid in there, and the distance to this guy. In order to know like which Boids are inside the neighbor range, let me draw a little Boid in here so I can draw the neighbor range here. If this is the Boid here, I'm going to draw a little circle around here, and I'm going to see that the only Boid that's my neighbor is this Boid here. All these other Boids are outside the distance thing. So like if I have, we'll say 3 Boids, the number of distance calculations you need to do is actually 3 multiplied by 2, because every Boid needs to calculate its distance to the other 2 Boids, and then because there's 3 Boids, every Boid needs to do that, so that's basically 6. The actual complexity of this algorithm is, it's written as O(n) squared. It's not exactly O(n) squared, it's actually O(n) n minus 1. Okay, so that's the actual complexity, because if you have 3 Boids, it's 3 multiplied by 2 calculations that need to be made. So if all the Boids are pretty spread out, then, you know, obviously I'm not interested in these Boids. I don't care about Boids that are miles away. I only care about the ones that are within my neighborhood. So how the cell space partitioning algorithm basically works is the environment gets divided up into cells like this. Should probably use a different color. So it gets divided up into cells like this. So cells are equally sized, right? You got the cell spacing, and then looking at this guy, well, there's no point even considering these because they're too far away. So with the cell space partitioning algorithm, the cells are kind of numbered like this, or whatever way you want to number them. Every Boid gets assigned a cell. So you've got one algorithm that's O(n). I'll change it to the black pen. One algorithm that's O(n), which is basically to go through every Boid. So you got 1,000 Boids, you have to assign every Boid to a cell. And it assigns every Boid to a cell. That's the first bit. And then what you kind of do is you just look at the current Boid, the current cell for the Boid, and the adjacent cells for Boids, and those are the ones that you consider in the distance calculation. So that eliminates, in this example, this guy and this guy, you know, and I only calculate like these. Let me draw that one and a different one here. I only am interested in these adjacent cells. So that's all I'm interested in for this one particular Boid. And that's how the algorithm reduces the complexity. That's how this algorithm reduces the overall complexity of Boids. The limitation of this, of course, is if the Boids are all in one cell, or they're all clumped up into one big school, then you still have to calculate like every Boid to every other Boid, because every Boid is a neighbor to every other Boid. But if they're all spread out, this could really speed up the algorithm. And you can see when I did that example right at the very start, and I enabled and disabled the algorithm, when the Boids are all spread out, well, this really speeds things up like by maybe 3 times faster. You know, so if ever again you have the pleasure, as I have done, of implementing Boids many times, as soon as you get your cell space partitioning algorithm working, it's actually very, very satisfying, to see the huge jump in performance this algorithm provides. So that's cell space partitioning, right? Actually, where were we? What was the question we were actually answering there? Yeah, that's how the cell space partitioning algorithm works, and that's how it can reduce the computational complexity. The limitation of this algorithm is if all the boids are clumped up, then every boid is still calculating its distance to every other boid, because every boid is a neighbor to every other boid, and so it's still ON squared. Okay, that's the limitation of it. How are boids assigned cells? This is very interesting. Do you need to go through every boid, get its position, compare its position with the bottom left-hand corner of every cell and the top right-hand corner of every cell, and say if it's inside the cell, then assign it to that cell? Do you have to do that? And then go through that like for every cell? No is the answer, because that's really inefficient. You can actually just do it by a little simple bit of maths. You can figure out what cell it is from the position, and I'll show you how that little bit of maths works. This is how you basically figure out the cell ID from the position. So let's look at that code. So the job that does that is called partition space. So let's look at partition space job. Partition space job, here we go. Okay, here is the magic of partition space partition space job. Here is the partition space job. No, that's the count neighbors job. Let's find the partition space job. Partition space job. Look, it's so simple, right? So, first of all, there is a native multi-hash map, right, which is this multi-key, multi-value data structure. And it's going to hold all of the boids that are in every cell. The key for this is going to be the cell ID, and then the value is the ID of the boid. So that's how the native multi-hash map is set up, right? And as you can imagine, you can have lots of boids in every cell. So like if the key is 1, there could be lots of values associated with that key. There could be lots of boids in cell number 1. So that's why it's what's called a multi-hash map. A multi-hash map is a multi-key, multi-value data structure. Does that make sense for everybody? If you don't understand that, what will be kind of interesting? Just say in the chat if you've ever heard of a hash map, if you've ever heard of a multi-hash map. Just say in the chat if you've ever heard of those two data structures. And here's a question for you in the chat. If anybody's still listening and paying attention, what is the computational complexity of retrieving a value from a multi-hash map or a hash map? What's the computational complexity of retrieving? Say I want to retrieve a value from a key. What's the complexity of the algorithm? In a hash map or a multi-hash map? I know there's like a 10 or 15 second lag, so hopefully by the time I finish talking, I'll see the answer popping up in the chat. Okay, here we go. So this is the thing basically that converts the position to a cell ID. So I take the position, the cell size is basically the size of every cell in whatever Unity units, and this is the grid size. The grid size, I don't think, it's just a multiplier, right? What you basically do is you take the x coordinate divided by the cell size, and that's going to give you the column, and then you take the z coordinate divided by the cell size, and then that gives you the row. And why did I multiply by grid size? I don't think grid size is particularly relevant. I can't really remember. Yay! Good man! It's actually O1 complexity in a hash map, if I remember correctly. Thank you. It's actually not O1. It's actually O log n. But good one. It's O1 for an array, and it's O1 for retrieving a value from a list. It's O log n for retrieving something. But an O log n efficiency is really good. It means something that you can call every frame in Unity without there being any issue. So anyway, this is basically taking row and column, and then yeah, the grid size is a kind of a multiplier. I can't really remember what grid size is for. But anyway, I suppose it's like how many cells there are across, you know. I don't know. Oh, it kind of needs grid size. It needs grid size. So anyway, yeah, I think this is basically saying that like this is going to be the column, and then the row is going to be the number of columns multiplied by the row. Yeah, that's it. And then it's the same thing for 3D. Because it's 3D, if you want to use 3D cells, you can test it. It doesn't really radically improve the performance, but I put it anyway. So this is going to be the row, this is going to be the column, this is going to be the row, and then this is the slice, if you like it. So this is the number of columns, and then this is going to be the number of columns multiplied by the number of rows. So that's how you basically assign a single number from the x, y, and z coordinates, right? And that becomes the key. So then, for every this is iterating over every element in the positions array, because everything is previously copied into the positions array. It's iterating through every element and then adding them to cells. And this is how you add something to a native multi-hash map. You just call cells.addCell, okay? And then you pass in I. So this is the partition space algorithm implemented. Next question. Cool. Limitation, partition space uses a native multi-hash map. Cool. How do boids access positions or rotations of other boids? Great question. So, lots of boids need to, like for example, when count neighbors is the next job that executes. And count neighbors goes through every boid. This is it here. There's two versions of this. One that uses the native multi-hash map if it's made. And then one that this is the simplest one to understand. I'll just explain this one first of all. So this is count neighbors, and this is just for me going through every element in the positions array, which holds the positions of every other boid. And then you get the distance, check to see if it's later than the neighbor distance. And if it's less than the neighbor distance, I add it into the neighbors array at the appropriate position. So the neighbor start index is going to be like the boid multiplied by the number of neighbors that it has, plus the neighbor count. So this is like every boid can have 50 neighbors. All the neighbors are stored in a big giant array of size 50 multiplied by the number of boids. So this is counting the neighbors. This is counting the neighbors using the native multi-hash map. So using a native multi-hash map, I only look into cells which are adjacent to the cell that the boid is in. So I look at the cell that the boid is in, and I look at the adjacent cells as well. And so I basically write this little 3D, three nested for loop thing. This is how you retrieve values out of a native multi-hash map. It's a bit of a weird thing. It uses the iterator pattern. So you go try first, get first value, and then try next get value, and you put it inside a do while loop. If you look up native multi-hash map iteration, this is basically how you iterate over it. So that's that. Oh yeah, okay. Which design pattern for retrieving all values that match a given key in the native multi-hash map iterator? It's what's called the iterator pattern. So you go try get first value, which returns a boolean. And then you go into a do while loop to retrieve the remaining ones, and you use this try next get value. It's called the iterator pattern. Where does the algorithm store neighbors for every boid? It stores it into the neighbors array. So like I say, the neighbors array is of size, the number of boids, like 1,000, multiplied by the maximum number of neighbors, so it would be like 5,000. And then every boid gets 50 elements from that to store its neighbors in. That's the maximum number of neighbors each boid can have. What happens if a boid has too many neighbors? If a boid has more than 50 neighbors, it only counts the first 50 of them. Cool. In separation job, what can cause the force to be NaN? So now we're getting into the implementation of the jobs. So let's look at separation job. Separation job. Separation job. Here's the actual job. What can cause it to be not NaN? You might even guess this already. If you guys remember how the separation job works, a force gets generated in the direction that brings you from the neighbor to the boid. So it's going to push the boid away from its neighbor. That's the direction of the force. And the magnitude of the force is going to be proportional, or is it inversely proportional? Inversely proportional to the distance. So the further away it is, the smaller the force. Yeah, so that would be inversely proportional. So here's how the algorithm works. So yeah, this is getting the to neighbor, which is the magnitude. To neighbor, yeah, which is the vector that brings me from the neighbor to me, and then you normalize that vector to make a direction, and then divide by the magnitude, or multiply by 1 over the magnitude, which is to give you the inverse, inverse of the distance. And here's what you need to check, right? This behavior could potentially return null if two of the neighbors have exactly the same position, and then the magnitude is 0. Because when you try and normalize then the to neighbor vector, what do you get? You get a divide by 0. So that's what can cause that to be 0. So you have to check to see if the magnitude is greater than 0. I discovered that this can occasionally return an NaN if two boids are exactly the same position. Then this behavior can return NaN. Okay, how does cohesion work? Cohesion works, you guys might remember the diagram. Every boid in the neighborhood, you get the average position and then generate a force to steer towards the average position. So let's look at what that looks like in code. That's called cohesion. Cohesion job looks like this. Here's the actual bit of the cohesion job here. So you go through all of the tag, everything that says tagged count, that's the neighbors. Getting the neighbor, getting the position, and then summing all the position vectors into this vector called center of mass. And then checking to see if there's neighbors. Again, you need to do this, otherwise you get an NaN, because you're dividing by the tagged count here. And if the tagged count is 0, if a boid has no neighbors and you try and calculate this, and you get a divide by 0. So this is another thing that can generate NaN. So the center of mass divided by equals to the number of boids. This gives the average position. And then this is seek. So you just return seek to the average position. That's cohesion. What's the next thing? We're doing really well here. In alignment job, how are the forward vectors for each boid calculated? This is interesting because we don't have transforms. We don't have transforms. So what do we have? We have a quaternion which gives the direction. So how would you get a forward vector from a direction quaternion? You're going to take the vector 3 dot forward and then multiply by the quaternion, and that's basically how the forward vectors for each boid are calculated. There's other ways to do that, but that's how I did it. You can also get it, I think, from what's it called? Is it the render bounds, or there's some other component I think you can get it from. Anyway, this is how I did it. Let's have a look at alignment. Here's the alignment job. Cool. So again, this is just using quaternion arithmetic. So you can take the rotation and then multiply it by vector 3 dot forward, and that will give you, from world space to the local space. This gives you the forward vector for that entity. Taking its quaternion and multiplying by vector 3 dot forward. Bit of quaternion arithmetic. And so here we go. We're basically, this is how alignment works. What's happening is a force gets generated that pushes the boid towards the average forward vector of all the neighbors. So here we're getting the average forward vector, and then dividing it by that, and then we're returning desired minus my current forward vector, and again using that quaternion arithmetic to calculate the forward vector for this current boid. So I don't need to store them all in a separate array or get them anywhere. If I have the rotation, I can calculate the forward vector easily. So that's that one. Now, what's the next? How's the force generated? There we go. What algorithm does Boyd job use to combine all the forces? Well, you know this. This is weighted, truncated, prioritized running sum. That's the algorithm that gets done. The code for this is a bit messy. I'm sure this could be cleaned up. I know it can be cleaned up. In fact, I know there's a slightly better way to do this. But if you look at the Boyd job, right? Here's not the Boyd job system, the Boyd job itself. So here's the Boyd job. So accumulate forces. It's using weighted, truncated, prioritized running sum. There's no polymorphism going on here. So all of the behaviors are just included here. And then there's the Boyd thing, and I'm summing up all the forces. If the force exceeds the maximum force, clamp the magnitude and return the force. So that's the algorithm implemented in a not very beautiful way. How is the Boids rotation evaluated? Well, that's the same as we did when we did this using mono behaviors. It's done using banking. So with banking, a little bit of the acceleration gets added to the up vector, so that when the Boyd is like going in a particular direction, you know, it's going to accelerating towards something which is to the left or to the right. It's going to bank a little bit to the left and the right. So that's that algorithm there. That's the banking algorithm. The spine system, what is the purpose of? With native, disable parallel for restriction. So this is something you'll see all over the place in my code, but you'll see it here. Look, with disable native parallel for restriction on positions and rotations. So this is an annotation that you can put onto your native array data structures. And with this annotation, it allows you to read the native container out of order. So if this thing is executing over, you know, entities with a spine, a translation, and rotation, and it's doing them in like 1, 2, 3, 4, 5, 6, 7, 8, 9 order, whatever, this allows you to read the arrays out of order. And if you don't put this thing here, the type system, not the type system, the race condition prevention thing in Unity says, hey, look, you're iterating over entity 500, but you're trying to read native array position 450. You're not allowed to do that. You have to read only native array position 500. To get around that limitation, you put this annotation in. So that's what its purpose is. What jobs does the spine system schedule, and what do they do? The spine system schedules just one job as far as I know. Oh no, 3 jobs. The same thing, copies all the values into native arrays, and then schedules a job that implements the spine animation thing that we did in semester 1, and then another one to copy all the native arrays back. Hey, there's a little artifact that you'll occasionally see. I don't even know if it's worth like exploring this, but when you run the thing, don't forget, like the spine system and everything is executing in parallel now. You know, the spine system previously, this guy moved, then this guy moved, and then the next guy moved, and then the next guy moved. But with this spine system, this guy might move, this guy might move, this guy might move. And in parallel, the other bits of the spines are also moving. So that introduces a very small artifact, which I don't really care about, but it's just interesting to observe. If the job batch, is the size of the job, doesn't exactly line up with the length of the spine, then maybe half the spine could be executed in one job and the other half of the spine could be executed in another job. So occasionally with the spines you see very small gaps in the spines. I can see one over there to the left. If you kind of explore it for a while, you get really small gaps, and that's because of that little artifact due to the batch size. I don't know if that makes sense for you guys, but I found it interesting. Let's go, we're nearly there. What parameters control the damping on the spine, and what effect will changing these parameters have on the spines? That's very easy to test. We can actually test it in the thing. So it's bond damping and angular bond damping, same as we did with the thing in semester 1. When we programmed the spine system, there were those parameters. So there's that job there. If you change the angular damping, well, you could just change the bond damping. It's like 0, 1. What happens if I make that like a 10? I don't know, 20. It doesn't seem to have a massive effect. The angular damping, maybe if I make that, it's definitely going to do something. 0.1. Ooh, no, that doesn't. That's nothing to do with it. Oh, there we go. Look, you can see now. that's the effect that it has, right? When you make the angular bond damping smaller, it's affecting the lerp and the slurp, right? So it affects like how the spine, how quickly the spine bits like rotate and move towards the previous spine bits, right? So it affects the lerp and the slurp. Here's the lerp and the slurp, and here's bond damping and angular bond damping. Almost there. Native container system job create. Positions and rotations. Head and tail system. What controls the speed of the procedural animation? And how does the head animation... Oh, I'm not even going to do this today because it's actually quite complicated. Because it basically does the equivalent of a rotate around. Oh, we'll have a quick look at the code. But if it's too complicated to explain and I can't explain it in 2 minutes, I'm going to leave this question as future work. It's one of those things where I wrote the code and I was very clever and I totally understood it, and then I looked back at it a year later and I'm going, oh my god, what does that do? I would have to draw a diagram of it again. Anyway, the head, what controls the speed of the procedural animation? You can again run the thing in Unity and see. Want to do maximize. So these guys are all procedurally animated using a harmonic function, and I'm pretty sure it's, where is it? I saw it there a minute ago. Animation frequency. I think if I was to make that a big number, like 1, watch what happens to the speed of the heads and the tails. There they are, yes. Just animating really, really quickly, right? So that's one parameter. It's the animation frequency. It's also the speed of the boids. So the boid speed gets multiplied into the animation frequency. So if the boid is traveling at a faster speed, the animation will be faster. If the boid is traveling at a smaller speed, the animation will be slower. So again, check this out, right? Actually running the thing, and one of the things I can change here is the overall speed. So if I change the overall speed up really fast, can you see from the thing that the animations now are happening really, really quickly? The Boyd updates obviously are happening fast, but also those guys are basically oscillating back and forth really, really quickly as well. So it's this speed thing, and then also the animation frequency. There's the 2 parameters. I'll just quickly show you the code for the head and tail system and see if I can remember how it works like in like just a minute or 2 of looking at it. Look at that. This is basically how the animation system works. It's this line of code here. So I'll see if I can draw like a diagram in 2 minutes, but I'm not going to explain it too much because I actually want to finish the class just by looking at the boys one more time. Here's the whiteboard. The animation kind of works like this, right? Here is like one thing here, one segment, and then there's another segment here. And if I was doing this in Unity with game objects, you can even do this, by the way, with entities. This guy is the boid. This guy is the head. And what I actually want to do here is like I want to rotate the head. So the head's going to like oscillate like this way and this way. But I don't actually want the head to rotate like this. Let me draw it in a different color. I don't want the head to rotate like this. Let me draw it in a different color. Because that's just rotating around its own center. What I actually want to do is I want to rotate it around this point here. I'll just put the point in. I want it to rotate around here. So how you would normally, or how you could potentially do that in Unity, Unity has an API call called rotate around. And I don't recommend that you use it very often, to be honest with you, because one of the things that happens if you call rotate around, you can actually pass in like where you want to rotate around. Normally when you call rotate, you rotate around the center of mass and it uses parenting and everything. If you call rotate around, you can say rotate around a different point which is not my center of mass. One of the things why I kind of maybe think this method is a bit dangerous is because I've noticed, like I've done procedural animations using rotate around, and it loses precision. You know, so like I remember programming dolphins at one stage, and the dolphins would swim like this, and then you look at them 5 minutes later, and then the head would be here, and the body would have like moved up to here, and they'd be doing this terrible thing. And then, to be honest with you, for a thing that's all about meditation and relaxing, it was quite traumatic to see the dolphin swimming around using that crazy thing. But anyway, that's essentially what I want to do. I want to rotate like around this point. I want to rotate this thing around this, which means updating the thing's position. So the thing's position is going to go to the left and right, plus it's obviously its orientation. So you can see now, if I actually rotate this around this point here, its position is rotated off around here, and its position is rotated off around here. That is these lines of code here, and because we only have 2 minutes left, I'm not even going to try and explain them, but it's the spine ID, this is the head, plus the rotation of the head, multiplied by vector 3.forward, so this is going forward like a half a thing up here, and then rotating the forward vector, plus vector 3.forward, multiplied by size, multiplied by 0.5. Oh my god! Now I understand what's happening. What this is basically doing is it's taking this rotation and then calculating the position by rotating the center point over to here. Okay, I did understand it. Listen, you guys, we're at the end of the class. Let's conclude with one more look at the beautiful boids swimming around in harmony. Thousands of them and thousands of them, you know, at like massive SPS, because we're, you know, have managed to figure out how to do all of this using entity component system, even get around the fact that there's no trails in ECS by programming like our own trail renderer system based on, you know, the little algorithm that we wrote in the first semester. You can control this thing with an Xbox controller by pressing various different keys, and, you know, you can turn off this like coroutine so that everything slows really down and you get right in close to it, and then you can explode it out like this, and it's just great fun to explore. And I like the look of it so much, I even got some t-shirts printed up with these you know, screenshots from the final build of this thing. And like I say, it's just great fun to play around with. It's basically why I think boids are so amazing, you know, because you can make all of these lovely looking things out of them, and it's so satisfying. Anyway, you guys, that's the end of today's class. Hope you're all still there on the live stream. Thanks for coming and joining today. Tomorrow we'll do the avoidance behavior. We'll do the avoidance behavior using mono behaviors. And that's it for today, you guys. Alright, enjoy the rest of your day, everybody. Bye!